I'd like to introduce our speaker tonight. So I'm very pleased to have our speaker. You're going to love this. Our speaker tonight is Bruce Bjornstad. And Bruce did his undergraduate work at the University of New Hampshire and his graduate work in Eastern Oregon. Excuse me, Eastern Washington, important, okay. His career as a hydrogeologist included being senior research scientist at the Batala Pacific Northwest National Laboratory. Since retiring, Bruce has had the time to reconnect, time and energy to continue his work in Eastern Washington. He's collecting visual evidence for floods of unimaginable proportions in a landscape that he knows very well. So join me, please, with a congratulation and a welcome for Bruce Bjornstad.
All right. Thank you, Sheila.
Okay, and you can share.
Okay. Here. All right. Is that coming through okay?
Yeah, looks great.
Actually, that's the beginning of the slideshow. I don't want to. Let's see. I'm going to have to scroll back. Sorry. So while I'm doing that, I'd like to acknowledge two of my mentors who are actually listening with us tonight. One is Vic Baker at the University of Arizona, has worked and helped me over the years on these ice age floods. He's one of the leading experts around the world on ice age floods. And then Eugene Keever. Dr. Keever was one of my advisors at Eastern Washington University, and helped me with my master's thesis in 1980. And we co-authored a book a few years ago on the trail of the ice age floods for the northern area of the Scab land. So I'd like to acknowledge them first. But here we are at the beginning of the program, and a classic picture of the Dry Falls area, looking south. If you've ever been to Dry Falls, you've probably been to the visitor center, which is over here, Highway 17. Runs along this plateau here. And you can look out across this beautiful Cataract Canyon. And most of what you're seeing is just this part of the canyon. You're not seeing most of this Coulee, another cataract, dry waterfall over here. And then beyond that, you have miles and miles of scab land going all the way down into southern Washington, along the Columbia Gorge and out to the Pacific Ocean. So it's a huge area, and really the only way to really appreciate the scale of these floods is to get up high, because the scale was so huge. You really can't see the forest through the trees per se, because the evidence is only becomes apparent from up above more often than not. So there were three sources for these ice age floods in the Pacific Northwest. Down in northwestern Utah, we had one flood from Lake Bonneville that occurred about 18,000 years ago. That went down the Snake, joined the Snake River, went all the way down into Tri-Cities and down the Columbia Gorge, out to the Pacific Ocean. We had another smaller flood from glacial Lake Columbia that occurred at the very end of the Ice Age. And then we have the Lake Missoula floods coming from glacial Lake Missoula. And by far, glacial Lake Missoula is the most important flood source, because it failed repeatedly over and over again, dozens of times during the last Ice Age. Whereas the Lake Bonneville flood only occurred once, in between some of the earlier Missoula floods, about 18,000 years ago. And then the Lake Columbia flood only occurred once too, also after the Okanagan Lobe ice sheet of the Cordilleran ice sheet broke up and allowed Lake Columbia to drain and go down the Columbia Valley. So my book that I'll be talking about later features all three flood sources, but tonight, because of time And, and just the fact that Lake Missoula was overwhelmingly the most important source, I'm going to be focusing mainly on Glacial Lake Missoula floods tonight. So the rest of the program will be on Lake Missoula floods. Here's kind of a simplified diagram showing you the elements that went into the Lake Missoula floods. Lake Missoula is up here, which formed when a Purcell Trench lobe came down the Purcell Trench from British Columbia, came down into the Sandpoint area of northern Idaho, and one lobe went up the Clark Fork River and created an ice dam for Lake Missoula at about the Idaho-Montana border right here. And another sublobe of the Purcell Trench went down into Lake Pend Oreille of northern Idaho. This is about as far as the ice got. And during the Missoula floods, this portion of the ice dam would break apart for questionable reasons. There's still some controversy about how it actually failed and drained. But we do know that that ice dam had to have failed very suddenly to allow all that water to drain out at once, draining Lake Missoula in about a matter of 3 days or less. And as it drained, it went down into the Spokane River Valley, Spokane area, and encountered another glacial Lake Columbia down here, which was already backed up behind another lobe of the Cordilleran ice sheet. And it didn't take much water from Lake Missoula to overfill Lake Columbia and force it to spread out and go through what we call the Channel Scabland of eastern Washington. And all that water converged onto one little opening down here, which is only a couple of miles wide, called Willamette Gap. You can see here it's spread out for almost 100 miles across eastern Washington. But when all that water was funneled into Willamette Gap, the water backed up, creating a huge lake behind the Willamette Gap called Lake Lewis. And then eventually, within about 3 weeks, all that water from Lake Missoula had drained through Willamette Gap, down through the Columbia Gorge, down into the Portland, Vancouver Basin, which is your area down there, which is off this map, and eventually out to the Pacific Ocean. So what I'm going to do today is I'm going to take you on a tour of these ice age floods, starting with at their source for glacial Lake Missoula, going through the area of the ice dam, and then going out onto the Scabland and all the way down through the gorge into the Portland area, and then on to the Pacific Ocean. A 600-mile trip altogether. So there's the ice dam, and what happened periodically, not just once, but perhaps as many as 100 times during the last glacial cycle. Lake Missoula, we think, failed as many as 100 times. And it would reform probably in a matter of a few dozen years. That ice dam would reform. It would continue to move forward and create a new ice dam for Lake Missoula, and then the same thing would happen all over again, over and over. So there's an example of one of the Lake Missoula floods breaking through the ice dam and then spreading out into the Spokane, Columbia River valleys, across the Scabland, and down the Columbia Gorge. Well, the last flood we know of from Lake Missoula was about 15,000 years ago, but there were many before that, and there were previous glacial cycles going back all the way to the beginning of the Pleistocene, which has been dated at about 1.5 million years. We have solid evidence that there was earlier floods as old as at least 780,000 years old within the Channel Scabland. And they may go back all the way back to the beginning of the Pleistocene at 1.5 million. There's a long list of flood features that are characteristic, diagnostic of these ice age floods. A lot of these are features you can see elsewhere, normal river and various environments. But the scale of the flood features is usually many times larger, hundreds of times larger than the features you see normally in a river environment per se. But anyway, for the rest of the talk, I'm going to be discussing a lot of these different features that I've listed here and showing you examples of these. So the Ice Age floods were the brainchild of J. Harlan Bretz, who back just about 100 years ago was doing field work in Eastern Washington. He was a professor at the University of Washington and was able to get over here occasionally to do field work. He was intrigued by the unusual landforms that he identified on maps of this area. So he came over in the late 19 teens and early 20s. He came and started doing field work in Eastern Washington, and especially in the Channel Scab land. And after several years of doing field work, he could only come up with one explanation to describe what he saw. And he proposed what at the time seemed like an outrageous hypothesis, and shook the geology profession to the bone. And his interpretation and outrageous hypothesis was that the only genetic interpretation proposed, which is inherently harmonious and which fits all the known facts, is that of a great flood of water. And here he was proposing something akin to Noah's flood, which at the time geologists were outraged by, because it was kind of taking us back to the Bible and biblical times and and Noah's flood theory. And Bretz, a lot of people saw Bretz as a heretic for putting us back in the Dark Ages, when in fact 40 years later he was awarded the Penrose Medal as the most outstanding award you can get from the Geological Society of America. So this is a aerial photograph taken in 1972 from a satellite, and from that you can really see the channels of the Channel Scab land. These dark lines running through this lighter foreground are places where the floods came through and they removed all the topsoil, all the wind-blown loose soil that covered the basalt across Eastern Washington. And if people had seen photographs like this back in Bretz's time, people would have probably come around to Bretz's ideas much earlier. But in 1923, Bretz had already figured this out. And he actually published a map showing you where all the channels were, and where the various deposits of sand and gravel deposited by the floods were located within the Channel Scab land. And he did this all from the ground. He never got off the ground or out of a motor vehicle to see any of this. But he was able to combine all the information he had gathered and visually see it in his head of what it might have looked like from space. So now I'm going to start sharing some of my photos and videos of the features that were left behind by these Lake Missoula floods. And initially, I'm going to take you to Lake Missoula. We don't see the whole thing here. It actually extends for 200 miles back up into Montana. But I do show the lower end of Lake Missoula and the ice dam that created it, and the lobes of the ice going down the Clark Fork River, as well as going down into the Pend Oreille River Valley, Lake Pend Oreille area. And the Spokane Valley, which was filled with glacial meltwater from waters backed up behind behind the Okanagan lobe of the Coeur d'Alene ice sheet, which is off this image to the left. And then beyond that, to the southwest is the Channel Scab land, which I'll be covering more subsequently. Okay, so how do we know there was a Lake Missoula? Well, it's obvious from the Missoula Valley. From the town of Missoula, you can actually see the strand lines that were left behind. These parallel lines you can see etched into the hillside are lines that were left behind by the lake waters that were running up against the shoreline of glacial Lake Missoula. There's dozens or hundreds of them. They go up to 4,200 feet elevation and then they stop. So that tells us how deep the lake was. It was about 2,000 feet deep at the maximum of glacial Lake Missoula. And beyond that, downstream of that, the floods were forced to go through an area called Camas Prairie. Okay, and this is an area where we have a couple mountain passes, Markle Pass, Winds Creek Pass is over here. These are places when the lake suddenly dropped and started draining. All that water was rushing to the exit point to the west, trying to get out of Lake Missoula all at the same time. And that generated strong currents within the lake that drained through these two passes. And as you'll see in a minute, I'll share the video showing you where there was erosion that took place in the passes because of all the scouring and the funneling of the water through these narrow openings. But then when the floodwaters, the draining floodwaters got out into Camas Prairie, they were allowed to slow down and spread out. And they deposited a lot of the sediment they were carrying and ripping out of these passes out onto these giant current ripples. And you can see these parallel lines are the ripples that were left behind by the draining floodwaters. Here's a highway for scale. So you can see the scale of these ripples is huge. Here's Markle Pass. Here's a beautiful bar that was deposited just downstream of the pass from debris that was ripped out of the pass, creating this beautiful expansion bar just below Markle Pass. This is Wills Creek Pass. This is that other pass. You can see if you trace these ripple marks, they go all the way back to the origin for the waters going through the passes. The ripples naturally fall are at right angles to the flow direction. And then here you can see this is a place where a borrow pit came in and it excavated or quarried to the inside of some of these ripples on Camas Prairie. You can see the size of the material they were transporting by the floodwaters. Some of these boulders are, many feet in diameter. Some even the size of small vehicles. So you can see the energy transporting these sediments was immense to create sediment like this within these ripples. So this is looking back up on the Markle Pass again. So floodwaters were, they were coming out of the Little Bitter Root Valley, spilling through Markle Pass and then draining down into the Camas Prairie. And they deposited this beautiful expansion bar, this delta-like bar on the downstream side of Markle Pass. You can see the erosion, the scouring into the bedrock that was done by these floods as they came through the Markle Pass. Another feature of the draining lake waters was these eddy bars. These are gulch fills, which occurred along the margins of the valleys that were draining the lake waters from glacial Lake Missoula. So these are big piles of sand and gravel that were deposited in the slower waters along the margins of the valleys. And here's down here where the arrow is pointing is a place called Eddy Narrows. Okay, this is a very important feature because all the floodwaters draining Lake Missoula had to go through this one little opening. That was only 2 or 3 miles wide, and so it was one of the few places where you can actually calculate the depth and the speed and the volume of the floodwaters as they were draining out of Lake Missoula. Richard Foster Flint did it first in 1942. He published a paper and presenting some numbers on the depth and volume of water, duration of the floods that occurred based on the cross-sectional area. He could you could measure, and knowing the depth of the lake waters, 4,200 feet elevation, you could actually calculate how long and how fast the waters were moving out through Eddy Narrows to escape Glacial Lake Missoula. Since then, Vic Baker and Jim O'Connor and others, Terry Aldo and others have done modeling to refine Flint's estimates on the volume, depth, and speed of the floodwaters draining out of Glacial Lake Missoula. So this is Eddy Narrows. You can see it's a narrow valley, but it was part of Lake Missoula would actually fill this valley, and it went all the way up, high up into these hillsides on the sides of the valley. There was up to 4,200 feet elevation. There was waters backing up behind the Eddy Narrows. And here's a view looking west onto where the ice dam was, which was right along the Idaho-Montana border. This isn't a real photograph, obviously, because it's been 15,000 years since this scenario occurred. But this is a photograph that was taken by Dave Bennett, who was up in the Montana, Missoula area. And he took a picture from the air, and then he gave the image to a person who was good at doing computer graphics and actually put in the ice dam and icebergs and ice floating within a glacier like Missoula. But today, if you could see this area, it would be basically the Clark Fork Valley. It would drop all the way down to the river down here and go back up the other side. And down, I mean, right here at the ice dam, the flood waters were 2,000 feet deep for Lake Missoula. So the Clark Fork River was 2,000 feet under Lake Missoula, way down here in the bottom of the valley. But this is what it would have looked like just before one of these dam failures. So further downstream, down valley in the Clark Fork Valley is a nice quarry of where they're removing debris. They're removing rock basically for landscaping stone out of this quarry, and it's this rock called the Belt Rock, the Belt Supergroup. It's 1.5 billion years old. It's very hard, durable rock that's been around for a long time, and it's been metamorphosed under high temperature and pressure. So it's very resistant to any physical and chemical weathering. So when you see erratics or icebergs that had floated these rocks down with the floodwaters, you can see them all over downstream. And it's because they are so hard and durable that they're well preserved. So in the area where I live in the Tri-Cities, I've mapped erratics up on Rattlesnake Mountain, and about 15 to 20% are these belt rocks, mostly composed of argillite and quartzite, very hard metasedimentary rocks. And so here you can see the quarry operation. They're putting these rocks into bins for hauling off to use for landscape. But basically, a lot of the area in Montana that was underlain by floods, it was part of the Belt Supergroup. So most of the rocks are from that area. And here's an example of a boulder that's in the Tri-Cities where I live, up on Rattlesnake Mountain. This is a beautiful piece of argillite, banded metasedimentary rock, probably from an ancient river deposit, 1.5 billion years old. And even all the way down into the Portland area, in the Willamette Valley, here's a piece of argillite right here. This is called the Bellevue Erratic, and a lot of you may have gone there. There's a state park where you can actually park down at along the road, and you can actually hike a short trail about a quarter mile uphill to this knoll that has a beautiful ice rafted boulder of argillite sitting on top of a little knoll amongst the vineyards of the Willamette Valley. It's in the foothills of these are the Coast Range. Over here, Portland would be up here in this area. I'm zooming in, coming a little closer. There's the path you can walk in to get to it. Goes around. Stevo Minsky, an artist friend of mine, actually drew this painting showing how the erratic might have looked like while it was still melting out of an iceberg that rafted it into place within Lake Allison, which would have been the lake that formed within the Willamette Valley by the Ice Age floods. It's a big chunk. These pieces probably broke off one side of it. Okay, now we're going back to the ice dam for Glacial Lake Missoula. This is the Clark Fork River. During the Ice Age, the whole valley was filled with ice. Where the Clark Fork River drains into Lake Pend Oreille, this also was filled with thousands of feet of ice. Here's the lower end of the ice dam. Lake Pend Oreille would have been at the furthest extent of where the ice dam came to. There's Cape Horn Peak, Lake Pend Oreille. This is Restroom State Park, Farragut State Park over here. And then here, this is about as far as the ice got. The ice dam got down to about here, and then that's about as far as it got. You can see where it actually beveled, eroded the hillside over here. You can see this change in slope. That's probably where the ice was sitting, and it came out into the Restroom Prairie over the town of Bayview, and would have gone up against the side of Cape Horn Peak. And that would have been the terminus for the ice dam for many of the floods. Other times the ice dam moved back and forth over time, so it didn't always stay in one place. It would move forward and move back. But the ice dam altogether was up to about 30 miles long maximum from where Lake Missoula was all the way out to the toe of the land, to the glacier out here. And beyond, you can see there's a very flat plain. Okay, this is called Restroom Prairie. And that's the outburst area. When floods broke through the ice dam down here, they spread out into this wide valley of the Restroom Prairie. And there's no rivers or streams within Restroom Prairie today, which is unusual considering it's in a valley. But that's because there's hundreds of feet of flood deposits that were carried out by these floods moving out across Restroom Prairie. And those very coarse, gravelly sediments are very permeable. So any snow or rain, meltwater draining through these sediments are going to immediately just soak down into the water table. And there is a huge aquifer, a very prolific aquifer underneath Restroom Prairie that supplies Spokane and the Spokane Valley with most of its excellent drinking water. This is looking south towards Prairie. Okay, so here we're looking at the very southern end of Lake Pend Oreille again. This is a place called Idlewild Bay. It's a beautiful park. This whole peninsula is all part of the Farragut State Park. I highly recommend it if you've never been there. It's a great place to go and hang out, to camp, hike. There's lots of boating, obviously, is very good in this area. But I love this picture because you can really see how where the ice was sitting during the Ice Age. There's Cape Horn Peak over here. So there was time there was ice that went all the way near the top of Cape Horn Peak, and it connected over with this slope over here. So you can see this change in slope is probably where the ice was beveling and eroding the side of the valley here to create this very prominent beveled surface that you see here. So you can almost visualize the ice coming down here and then crossing over onto Farragut State Park and then back up onto Cape Horn Peak up there. Okay, so what I just showed you in the video was this area in here. Okay, this is Bayview. There's Lake Ponderay, and you can see where the ice came down, and it connected the mountains between here and Cape Horn Peak with ice, and that's about as far as the ice got. As far as we know, it may during earlier ice ages, previous floods, it may have gotten out further out into the Restroom Prairie, but we know it got at least this far. And when that ice dam broke up, all that water was allowed to go down the Restroom Prairie and into the Spokane Valley. And also, as those flood deposits were filling the valley, they actually raised the floor of the valley, and that blocked the tributary drainages coming in from the side. These lakes you see are streams that were blocked by the flood deposits that were filling the Restroom Prairie. So that's why we have all these lakes. There's 9 of them surrounding the Restroom Prairie. It's because of this buildup of flood deposits. Okay, so now we're going to move out onto the Channel Scabland. As I said previously, the floods were coming down from the northeast into the Spokane area. And it's not shown here, but there was an ice dam that I'll point out later that blocked the Columbia River across the Waterville Plateau, created a big lake called Lake Columbia, filling the Columbia and the Spokane River valleys with water, almost up to the rim of the southern side of these valleys. So imagine water coming in from Spokane into the Spokane area from the Lake Missoula, hitting a pre-existing lake in this area, and it didn't take much more water to overfill Lake Columbia, which is in this area, and then spill out across what we call the Cheney-Palouse Scabland Tract. And then there's another tract over here called the Telford Crab Creek Tract. And a third tract would have been through down Grand Coulee. Okay, so again, here's Lake Missoula, the ice dam. There's Lake Columbia, where all the Lake Missoula floodwater spilled into and then spread out across the Channel Scabland. But prior to the floods, most of eastern Washington was covered with these beautiful, let me back up a little bit, was covered with these beautiful rolling hills of Palouse soil. Okay, and that's this is windblown soil called loess, L-O-E-S-S, that covered and blanketed most of eastern Washington with dozens or even hundreds of feet of this windblown soil over eons during the Ice Age. So most of eastern Washington looked like this before the Ice Age floods, but later, when the Ice Age floods started coming out, then they started running over the tops of these hills and creating streamlined Palouse hills, as I'll be showing you shortly. So this is what it looked like before. This is what it looked like as and since the floods came through. These blue arrows show the pathways of Ice Age floods based on the locations of channels. Not only coming down these channelways, but also crossing over, spilling over these islands of Palouse loess and creating these beautiful streamlined bed forms that you can see here. They're usually blunt and steep on the upstream side and more tapered and gentle on the downstream side. And here's one of the islands that I'm going to show you more closer up in the video that follows. Okay, so this is that same island I just pointed out. You can see the scale of this. There's a road. Oops. Go back. Start again. So there's that island. You see the power line down here, and there's a road for scale. The road. So these hills are still very fertile, and farmers will actually grow their crops, mostly dryland wheat, on the tops of these hills. They're still great for growing crops, but down in between the islands, it's eroded down to bare basalt bedrock. So that's why it's called scabland, because it's no good for farming. Here's another series of streamlined Palouse hills down near the area of Palouse Falls. Notice they're all parallel to each other, and this is the upstream side of these islands, Palouse Islands. There's 3 of them here, so the floodwaters were flowing over across all of these islands simultaneously and eroding down into the basalt bedrock in between. Okay, so if you've ever been up on I-90 going to Spokane, it's right over here, and you've actually driven by this area probably before if you've been on I-90, and get this beautiful scab land that was carved out by the floods after they spilled into the Cheney-Palouse scabland tract. Mostly they did erosion, up in these areas where the gradient, where the slope of the surface was steeper. But you also had deposition going on over here. You can see there's there's a bunch of giant carved ripples that were left behind by floods that were coming across the scabland, and locally they would deposit sand and gravel in places, and quieter where the water was moving slightly slower, and they would deposit sand and gravel, and as the floods moved, they would transport that sand and gravel and mold them into these beautiful giant carved ripples that you can see here. And you can interpret the flow the direction of flow based on the ripple orientation. The flow is always at right angles to the ripples, so the floodwaters are moving from the upper right to lower left in this picture. So over on the eastern margin of the Janel Scabland is Rock Creek. It's the easternmost coulee within the Scabland and within the Cheney-Palouse tract. It's a beautiful canyon, but notice the size of the canyon compared to the stream that runs through it. This is Rock Creek. It's a tiny little stream. It is a perennial stream that runs year round, but it never gets much bigger than this, except during floods. It will occasionally spill out of its and overflow its banks, and maybe cause some deposition within the floor of the coulee. But this is definitely an underfit stream compared to the size of the coulee. So this coulee had to have been formed originally by, or been modified and deepened and widened during these ice age floods. Beautiful Bonnie Lake. You can actually take a motorboat or a canoe. You can actually paddle up along Rock Creek up into Bonnie Lake. And down below Bonnie Lake is Rock Lake. This is the deepest lake within the Channel Scabland. And nearby we have a sequence of parallel coulees, including Little Cove Coulee. And jumping over to Moses Coulee now, which is over in the western portion of the Scabland, up on the Waterville Plateau. This is a beautiful coulee, 50 miles long. It's just as big, just as long, just as impressive as Dry Falls and Grand Coulee, but it's harder, a little harder to get to. It's on, but you can take public roads to get in there, and it is open to the public, most of it. Here's a public road. You can see it here. It winds through the coulees. It's a place called Three Devils Cataracts. So imagine floodwaters in this, a giant flood coming through here. You probably, during that flood, you probably wouldn't have seen anything but these hills along either side of the coulee. Everything you see here in the foreground would have been underwater, maybe under tens or hundreds of feet of floodwater, and all that water was eroding the surfaces of the basalt and eroding down into creating canyons, deep canyons, coulees. Okay, so now we're over in Grand Coulee. This is the head of the upper Grand Coulee here. This is looking north. Grand Coulee Dam would be out of sight just up here along the Columbia Valley. This is the Northrop Canyon. This is a state park now that you can hike into. But you have a couple of really impressive short cataract canyons that are Castle Rock cataracts. You can see they're horseshoe shaped cataracts. And oftentimes they're separated by a blade of basalt, a ridge of basalt bedrock that didn't erode during these floods. But there was major erosion going on in the cataracts that receded upstream as the floods were coming down from the north. Castle Rock is here. You can see there's basalt capping granite. There's actually granite bedrock exposed along the base of the upper coulee. This is the other side of Grand Coulee on the west side. Waterville Plateau would be this side over here. There's Steamboat Rock. So the floods were coming from the lower left to the upper right. And continuing on down into Grand Coulee, we eventually get to Dry Falls area, which is this. This is Dry Falls. This is Umatilla Rock. This is another one of these blades of basalt that separates multiple recessional cataract canyons. The height of the coulee at Dry Falls is about 400 feet high. From the bottom to top is 400 feet. So the floods coming down the coulee were another 400 feet deep when they went over the falls. So you can imagine everything you can see in these images. Most of everything you can see would have been under hundreds of feet of flood water. So this is Dry Falls, Umatilla Rock. There's actually two, and the beginning of a third cataract, horseshoe-shaped canyon that developed here. So these cataracts form from recession. So as the floods were coming down, they would fly over the lip of the falls, and there'd be an eddy forming as the back flood of the water as it was dropping. It would erode the bottom portion of the cliff, the cataract cliff, and that undercutting would cause the whole face of the cataract to drop, and then it would start to undercut again. So eventually, these cataracts would work their way upstream, recessional. This cataract started further downstream, about 20 miles at Soap Lake. And after the last ice age flood, about 15,000 years ago, this is where it ended up. During the next ice age flood, this cataract would probably continue on receding to the north. You see the beautiful grooves that were etched into the basalt surface by these floods. Potholes were circular potholes formed by eddying floodwaters, circulating floodwaters along the base of the flow. This is dry falls up here. So looking in a little closer at the potholes, here's a sequence of them. They can be 100 feet apart and almost as deep as they are wide. And a lot of times they're overhanging. They overhang inside. If you fell into one of these, some of these, you would never get out if you survived the fall. There's a beautiful lake, deep lake. This is a scab land down below Dry Falls. There's another recessional Cataract Canyon that formed. Lots of grooves etched into the basalt surface. This is one of my favorite features called the Great Blade. That was Brett's coined the term Great Blade. And you would never know this feature unless you were able to get up in the air and see this, because from down below, and you're driving along the highway through the Grand Coulee, you look up and you see a wall of basalt, but you think it's the edge of the valley, and it's not. There's another valley on the other side. And in between is this beautiful narrow blade of basalt, and in places narrows down to just a few tens of feet, like this. So, and this, the floodwaters were overtopped even the height of the blade, as well as racing down either side. Lake Lenore is a beautiful lake, now carved out by the Ice Age floods. Here's part of the Great Blade, the southern end. Over here is the Great Blade. Waterville Plateau, and then the Coulee monocline actually folds down across the Lake Lenore. Spring Coulee, also known as Billy Clap Lake. And, it's Billy Clap Lake is a man-made reservoir now. It was dammed up for irrigation. You can see where some of the channels that were eroded, the floods. And here's some giant current ripples along the margins of the Spring Coulee. If you looked inside those ripples, you'd see a lot of sand and gravel. So now we're kind of in the middle portion of the Channel Scabland. We're in the Lake Creek area near Odessa, and near there with lots of lakes. This is actually Lake Creek Coulee, part of Lake. It's called Lake Creek Coulee because there's just a string of lakes all along the Coulee. Twin Lakes. There's one, Coffee Pot Lake is up here, and there's a whole bunch of others. So here's another unusual feature. It takes some explanation, and I'm not sure I have the time or want to take the time to explain the details of how these things form. But in summary, these originated when the basalt flows came out. We think they encountered some kind of moisture. Either they ran into a stream, or maybe a shallow pond, or a body of water that caused the hot molten magma to create steam explosions that interacted with the water that it was overtaking. And as it did so, it would form these dikes. These cracks would form within the lava flow, circular dikes, and then the still molten lava inside the lava flow would come up through those dikes to the surface, and then this central area would sag down and then cause more lava to squeeze up through these dikes, creating these what we call ring dikes. within the basalt. These all formed when the lava was coming out. And this happened, it happens to be about 15 million years ago for this particular, this is the Rosa lava flow. It's about 15 million years old. So we think that originated in 15 million years ago. But after that time, the lava eventually probably filled, or mostly filled, this little basin, and then it was covered with hundreds of feet of windblown soil, like we saw elsewhere on the Scab land, this polluted soil. And then later, still later, then the floods came through and they eroded the polluted soil, and they started eroding down into the basalt. And when they did so, they excavated out the weaker rock that was in between these dikes within the basalt flow. Therefore, we're looking at exhumed ring dikes that formed 15 million years ago that were exhumed by ice age floods. So that's in a nutshell. There's two kind of right next to each other. This is a few miles north of Odessa, Washington. HU Ranch Coulee is a spectacular canyon down in the southern Scab land near between Palouse Falls and Colotis. This is looking south. Devil's Canyon is another very straight canyon that formed parallel to HU Ranch Coulee, as well as the Palouse River Canyon. And these straight, the rivers or the canyons are straight because they follow tectonic fractures. These are weaker rock where the rock was broken apart by tectonic forces, creating these very linear cracks in the ground. So when the floods came through, they took the path of least resistance, and the rock was weaker through these fractured zones. So the floods preferentially eroded out these canyons, creating these straight lines. And now I'm going to, we're moving out of the Channel Scab land now, and I'm going to be talking about some of the deposits and features that were created by the areas south of Grand Coulee. This is where Grand Coulee emptied into a big basin called the Quincy Basin. It spread out, floodwaters slowed way down, allowing lots of deposition to occur in the Ephrata area. But when the floods came in out of Grand Coulee, there was so much water coming in so rapidly that it overfilled the Quincy Basin. Even though water could go through Drumheller channels, there was too much water for Drumheller channels. So a lot of the water, or some of the water, continually filled Quincy Basin and caused the water to spill over the west side of the basin through a place called Potholes Coulee and Frenchman Coulee. And so that's what I'll be showing you in these coming slides. This is Drumheller channels looking north in the direction of Grand Coulee. And you can see the beautiful Scab land that was created. This is all just bare basalt, bedrock, mostly channels. Here's a streamlined island of basalt that was eroded by the floods. The floods were moving from lower to upper part of the slide. And you can really see how the floods made a streamlined prow at the head of this island. And they excavated out the basalts. They found these basalts particularly easy to erode because of these beautiful columns of basalt, polygonal columns, so 50 feet long, 100 or several feet wide of columns that were easily carved out and plucked out by the Ice Age floods as they eroded this island. And this is Crab Creek today. This is a perennial stream, the only one that runs through Drumheller channels. Downstream of Drumheller channels is a place called Othello channels. This is another place where the floods couldn't go over the Yakima folds, so they went around the eastern edge of, in this case, it was the Saddle Mountains. So the floods went along the side of the mountains, and they spilled over a low point along the east side. So here's the Othello channels here, Grand Othello channels. These Frenchman Hills and Saddle Mountains were too big, too tall for the floods to go over. So they were forced to go around. Now here on the west side of Quincy Basin, there are these two parallel Cataract Canyons, one being, this is the Potholes Coulee. You can see again, it's a dual Cataract Canyon, similar to Dry Falls and many other Cataract Canyons. The southern cataract is the Dusty Lake Basin. The northern Cataract Canyon is the Ancient Lakes Basin. And then again, we have a blade of basalt running down the middle. This is a recurring theme in these Ice Age floods. And it's particularly, it has a lot to do with the fact that it's eroding basalt too. Floods don't always, basalt in particular, they tend to create these landforms, but other types of rocks often don't create these same landforms. Oops. So let's see, I gotta back up. I skipped something. Oops. Sorry about that. Okay, so I lost my place here. I really don't want to go back. Sorry. Okay, so yeah, now we're back on track. There's Potholes, Coulee, and the other Cataract Canyon that drains out of the west side of the Quincy Basin is Frenchman Coulee. And this is just a few miles south of Potholes, Coulee, and you can see where the floods came out of the Quincy Basin. They went up and over into Frenchman Coulee, and they drained down into the Columbia Valley, which was hundreds of feet down below. So there was a lot of hydraulic gradient across this short section, which is why the floods were able to erode so dramatically through this area, because of the extreme hydraulic gradient that was created. Here's kind of a nice row of basalt columns. These are called the Feathers, popular rock climbing place. So now we're going to look at some giant current ripples within the channel scabland. Again, these are depositional features and not erosional. So these are deposits of sand and gravel that were transported by the floods and then deposited into these very regular shaped undulating ripples. Giant current ripples, or dunes, some people call them. Here you can see there are ripples on three different surfaces. Those are an upper surface, a middle surface, and a lower surface. Crab Creek, again, for scale. There's some ripples along the Washtenaw Coulee. And you can see there's a borrow pit, getting lots of good sand and gravel out of that in that flood bar. The Babcock Bench is a feature over on the west side of the scabland. This is the Columbia River. This is near just west of Quincy, Washington. And Babcock Bench is a high bench of basalt that has some of the most bizarre erosional landforms I've seen anywhere. see if there's a common elevation for all these features. They were all, at one time, they were all connected. This is a single lava flow. When the floods came through, you can see they eroded down into the basalt, creating these unusual landforms. This is looking straight down. There's a Columbia River, which is 700 feet below the bench. Some beautiful potholes eroded on top of the bench. Babcock Bench is over here, and across the river is the West Bar giant current ripples. Some of the best you've seen anywhere. We think that the West Bar ripples had to have come from a flood from Lake Columbia, because there's no way they could have going across the Scab land into Quincy Basin and then gone upstream against the flow of the flood. So we think the glacial Lake Columbia is the source, or maybe another lake that we haven't identified yet up in Canada that might be the source for these giant current ripples. But they are just as impressive as any ripples you'll see out on the Scabland. Again, they're just composed of thick deposits of sand and gravel. Sentinel Gap is a place where the floods eroded through the Sentinel Mountain, the Saddle Mountains, into the Pasco Basin. And here's Sentinel Gap. And downstream of Sentinel Gap are there's a place called the Mattawa Fan. Lots of hundreds or thousands of the huge basalt boulders spread out below Sentinel Gap. Okay, so this gravel boulders, bouldery gravel, probably came from the floods ripping out of basalt, widening the gap, oversteeping the walls of Sentinel Gap and depositing them downstream onto this Mattawa Fan. Okay, so now we've come into the area of Lake Lewis, which is the water that backed up behind Willamette Gap. So all that water coming out of the Scabland, spreading out for 100 miles, all converged onto this one little opening called the Willamette Gap, only a couple, 2 or 3 miles wide. And at times there was twice as much water going in the gap that could actually go through at once. So that was a hydraulic constriction that caused water to back up for tens of miles upstream. Sometimes it might have gone all the way, backed up all the way up to Mount Moses Coulee, or Moses Lake, I'm sorry. And when the water was backed up, it reversed the flow of the Yakima River, and the floodwaters reversed all the way up to Yakima and beyond. It reversed the flow of the Walla Walla River, reversed the flow of the Snake River. So the floodwaters back flooded all the way up to Lewiston, Idaho. And the waters were up to about 900 feet deep in the Tri-Cities. The darker the blue areas was the deeper water. The lighter blue is the shallower water, and everything in brown was above the level of the floods. But here's Willamette Gap. The gap itself is only about a mile wide, but the floods actually overfilled the gap and caused the floodwaters to spill over on both sides of the gap for another mile. It's Two Sisters landmark within the Willamette Gap. And during the largest floods, the floodwater would have been another 100 feet over the very top of this highest point right here. There's Two Sisters again, looking downstream. Here you can see where the flood spilled over the sides of the gap. Not only were they in the gap, filling the gap, but they also spilled over, carving channels into the uplands on either side of the gap. There's a spillover channel right there. Lots of spillover channels the floods coming through. Okay, so now we're, after the floods went through a little gap, then they headed down into the Columbia River Gorge, pretty much followed the Columbia River the rest of the way out to the ocean, spilling over occasionally in places like this, Philippi Canyon. Okay, this is where the Philippi Canyon is. This is Scab land. It sits high above the Columbia River in I-84 that was in that previous video clip. The floods were coming into the Columbia River Valley, Columbia Gorge so fast, they were able to spill up and over the sides of the gap of the valley and carved scab land along the margins. You'll see here. So this is scab land. And then the water spilled up and over, and then they hit it, and then they descended down into the John Day Basin, and then back into the Columbia down here. So they took a detour, but to do that, they had to climb hundreds of feet up to get through this pass. And this is an eddy bar that formed along the inside of this side spillover canyon. This is sand and gravel deposits that were built up on the inside, a more protected, slower water side of the gap. There's that same eddy bar down here. So the water spilled way up into this area. They went over, carved all this scab land across the pass that went into John Day River, which was downstream. Maryhill Museum of Art along the Columbia Gorge. This is the town of Biggs Junction. So the floods coming down the Columbia Gorge, they would have probably been 200 or 300 feet deep over the top of the museum. They spilled over onto the sides of the gap, as well as filling the gap or filling the gorge. So this is a bench that's several hundred feet above the Columbia River. So the waters would have gone up into this to this height, filling the gorge up to here. Scab land along these benches. Here's a feature that most people have never seen unless you've been up in the air and fairly close to the ground. Here's I-84 going down the Oregon side of the Columbia Gorge. So we're looking let's see. So we're looking south here. This is the Deschutes River, where the Deschutes River comes in right here. And you can see that when you're driving along the freeway down here, you can look over and you can see a wall of basalt. That's all you see. You can't see any of this here. This is all scab land created by the floods coming down from the left to the right. And the floods were all the way, they went all the way up to this point here. You can see where they carved the margin of this wall and eroded the side of the sediment deposit up here, way up above the river. So this whole area was all underwater, hundreds of feet of water, and carving out scab land, beautiful etched out areas the floods created along tectonic fractures within the basalt. Here's kind of looking to the east. So here's a planed off beveled surface created by the floods. And they probably went all the way up to that point there. and some potholes around circular holes. Again, these are from colks or swirling eddies that form during floods, eroding into the basalt. So here's another feature just downstream of Celilo. It's a place called Fairbanks Gap. Okay, so Fairbanks Gap is a place where the floods are actually, they were coming down the gorge from the east. They've actually filled the gorge, had to have filled the gorge up to at least this height and probably further up close to the height of this ridge here before the floodwaters were able to spill over and carve into some sediment. This is sediment that's overlying the basalt here. So the sediment was easier for the floods to erode. So when they overtopped the ridge, they eroded down through the sediment until they hit the basalt underneath. And at that point, they couldn't erode as quickly. So the floodwaters basically eroded this U-shaped channel across Fairbanks Gap down into the basalt underneath. So here's like looking into it from the north, looking south. There's another stream drainage on the other side where the floodwaters drained into. And then eventually they rejoined the Columbia River a few miles downstream. So looking down. So the floodwaters had to have gotten up here and they eroded down into that rock bench. And that's about as deep as they were able to erode. And there's a nice U-shaped hanging channel looking into the Columbia Gorge at Fairbanks Gap. Okay, so further downstream is a place called Horseleaf Butte State Park. It's a beautiful little park managed by Washington State Parks. Some very unusual flow top of basalt flow. It's kind of distinctive in this area, kind of spindly basalt flow top. And then Horseleaf Butte is actually this prominent, this butte that sticks up down here. It's another place where you can go and hike. There's lots of hikes going off to the right, up along the sides of the gorge, as well as hikes going into the up to the Horseleaf Butte. There's the Dalles in the distance over here. Mount Hood, of course, beautiful Mount Hood in the distance. This is like we're looking over Horseleaf Butte to the east. This is okay, near the Dalles. You can actually see this from the Dalles from the highway. Are these strand lines or trim lines that were left behind by floods as they came down the gorge. There was some sediment deposited in places like this, and that allowed the floods to actually erode these little benches that you can see as they came down. They're probably these probably record some of the last floods coming down the gorge and creating those trim lines. Another place called Rowena Dells on the Oregon side of the Columbia Gorge. This is Rowena Gap, with the Dalles being just beyond that. This was another constriction for the Ice Age floods. Floods coming down from the Little Gap into the Columbia Gorge. When they encountered this gap, this was another pinch point for the flood. So the waters actually backed up, created a lake called Lake Condon, a temporary lake. It was only there for a few weeks or less. But nonetheless, it was a pinch point that backed up some water, and it caused the water to speed up a little faster as it went through the gap here. And just downstream is Rowena Dells, which is all these carved out coulee areas. There's some potholes eroded into the top of the basalt. Mount Adams in the distance. It's another state park, Oregon State Park. Lots of good hiking in that area. Well, wildflowers are beautiful this time of year. This shows the balsam root, yellow balsam root. And blue lupin is especially nice this time of year. There's a couple of those potholes closer up. Again, these are swirling eddies that created kind of drilled holes into the top of the salt by the Ice Age floods. Mima mounds, these little yellow green blobs are Mima mounds. Those are probably post-flood pattern ground that form maybe from freeze thaw activity or some other more recent process since the floods. Beacon Rock, another state park in Washington. This is a volcanic neck that erupted associated with Cascade volcanism, I think around 50,000 years ago. And it's more resistant rock apparently than the basalt that flowed in and around it later. But when the floods were coming down, they didn't overtop Beacon Rock, but they came close, probably within a few tens of feet, maybe 100 feet of the summit of Beacon Rock is how deep the water was. So you can see how big the gorge is and how much water had to have been traveling down through the gorge. There is a trail going up to the top. You can see the stairway switches back. Dozens of switchbacks getting up there. It's a great hike with lots of handrails. No, not much chance of falling off. Actually, there's a trail goes all the way to the very top up here. Okay, so that kind of ends the video portion, but I want to talk a little bit about the areas downstream. When the floods came down the Columbia Gorge, they emptied into the Portland, Vancouver Basin here. And there's lots of water still coming out of the gorge, enough that the water backed up behind another constriction down up here called Willamette Gap. And when that hydraulic constriction backed the water up, it forced water to backflow up into the Willamette Valley. And it backflooded through the Oregon City area, Willamette Falls, and it also backflooded through a channel at Lake Oswego. So this was the place where the floods were able to backflood up into the Willamette Valley, creating Lake Allison, which was a temporary lake. Only there again for probably maybe 1 or 2 weeks before all that water was allowed to drain out to the Pacific Ocean. But I want to mention a couple important unique type of erratics that are present in the Lake Allison area of the Willamette Valley.
And Bruce, we've had a request for you to show your cat.
Maybe, well, yeah, he's settled down in behind me. Could you see him or did you just hear him?
Just hear.
Yeah, he's sitting right behind the computer screen.
I thought it was my cat.
I'll show you here. Let's see him. I feel like Nick Zentner trying to.
Yeah, this is great. I'm going to ask you about your microphone in a minute.
So anyway, the Bellevue Erratic is an important erratic. It's one of the biggest in the Willamette Valley, and it's actually also a state park. And we talked about it earlier, in the talk when I was talking about the belt rocks up in northern Idaho, and the fact that it left behind those rocks all along the flood path from western Montana all the way down out to the to the Willamette Valley of Oregon. So there is a record of these rocks from Lake Missoula, all along the flood route. And this is a particularly good one because it's so big and so well preserved up here on this hillside. And again, I talked about the quarry where these types of rocks are removed today, but the Ice Age floods and the ice dam was actually removed these rocks on its own. And when the ice dam broke up and the floods carried that ice away in the floods, it rafted these boulders all the way down 600 miles away into Western Oregon. So, and the last erratic I'm going to show in the last major slide is the Bellevue or the Willamette Erratic, or the Willamette Meteorite. It actually is a meteorite. It's actually the largest meteorite found in the U.S., sixth largest in the world. It's a pitted iron nickel meteorite discovered in 1902. It's now in a museum in New York City, and that's where it's been since the early 1900s. If anybody wants to go see it, and when it was found on the hillside just south of the Portland Basin, between Lake Oswego and Oregon City, near the town of Willamette, which is down here. And it was found at about 400 feet elevation, which happens to be the high water mark for these Ice Age floods that came into the Portland Basin. They went up to 400 feet, and that's as high as they got. So it is at the high water mark. Plus, when they found the erratic, the meteorite, they also, people reported seeing other unusual foreign rock types that could have been, they were probably associated with other rocks that were rafted in on icebergs. So I think the evidence is pretty sound for this being an ice rafted boulder that was brought in after colliding with the earth, perhaps in the ice sheet for the Cordilleran ice sheet up in British Columbia. British Columbia ice would have ended up down in northern Idaho eventually. And when that ice dam broke apart with a Missoula flood, it could have easily carried this meteorite down in an iceberg, depositing on the hillside near Portland. So it's a great story, and one that I think is probably true. So in the last few minutes, I want to take a little bit of time for some shameless commerce. First of all, I have a YouTube channel with YouTube videos of Ice Age flood features. It's called Ice Age Floodscapes. A lot of the videos that I shared with you tonight, and many more, are located on this website. And I'm adding new videos on a regular basis as I have time. And you can subscribe if you go to the website, YouTube website. You can subscribe and automatically get notified when any new videos are available. And I've written a couple of guidebooks on the Ice Age floods, intended for the amateur lay person who's just interested in the floods and wants to go out and discover what they're about and actually see some of the features themselves and ways to get around on foot or in the car or in an airplane. These are guidebooks to do that. And Gene Keever is, I think, hopefully still listening with us, is a co-author on the second book that we did, published in 2012. And just out in the last few weeks is a new book called Ice Age Floodscapes of the Pacific Northwest. It's with Springer, which is a major international publisher of science and technology. They actually, they blew me away by actually contacting me. I didn't contact them about doing a book several years ago, and that actually followed through. And it's now available as a hardcover coffee table type book. It's mostly color photographs from the air. Not all, but most are from the air. And with captions to describe what's shown in the photographs. It's about 180 pages altogether. And it's available you can order it at springer.com or amazon.com. And right now you can order it. It's available to order, but the next shipment might be delayed because I think they're going to be changing printers. The first printing wasn't of high enough quality. So I'm waiting for them to come up with a better printer, and hopefully they'll produce a better product than what came out initially. So anybody who already bought the book, I apologize that it wasn't the quality it should have been, but at least you have it really, and maybe the publisher will allow a refund or a discount towards a new book. I don't know. We haven't discussed that. Anyway, that's the end of the program, and with that, I'd be glad to answer any questions. And I'll stop video. Stop share.
We have so many good questions this
Yeah.
time, boy.
Yeah, there's quite a few. I was thinking, starting with Gary, he had a number of questions about how you took the video footage. Gary, if you want to unmute and maybe, ask your questions, there's quite a few of them.
Okay.
Can you hear me?
Yeah.
All right. It's Gary. Hi, Gary.
Yeah, hi. I was just curious about whether this was aircraft or remote operated drone. Then I read your synopsis for this presentation. So it's some type of remote operated aircraft. Tell us about the aircraft, its size.
Yeah, well, all the video I showed tonight was taken with the drone. But a lot of the photographs, the still photographs I showed as well here as well as in the book, were taken with a fixed wing airplane. I didn't start doing drone photography until 4 or 5, 6 years ago. So a lot of my earlier work was taken from aerial work was with fixed wing airplanes, and more recently it's been with the drone.
Please tell us the make of the drone.
Oh, it's
Yeah.
I use a DJI Phantom 4.
Okay, thank you.
Yep. It's a
What's its
quadcopter.
altitude?
I'm sorry.
What's its altitude?
I can go up to a maximum of 1,500 feet. And it's
And how far-
programmed into the drone not to go any higher than that. And I've flown as far as maybe 1.5 miles away from where I started.
Wow.
So it has a pretty good range.
Thank you.
You're welcome.
So Paul was asking if he found a nicely rounded quartzite here in Portland. Is there a way to tell if it was rounded by the flood or was it a river cobble that ended up in glacial Lake Missoula?
Okay, if it's a well-rounded quartzite, my guess is that it would be probably a river. It was probably brought in by the Columbia River, because the Columbia River was draining areas that have quartzite. And if it's well-rounded, that's an indication that was probably river work.
Thank you. Thank you.
A lot of the floods, because they were so short-lived, they didn't have time to do much rounding.
So Bruce, if I find a rounded basalt, what is that telling me?
It was probably in a river. It came out of
Okay.
the river. Yep.
Thanks.
I had a question.
Mhm.
They were talking about they were not sure how many floods there've been. Have they looked at the sedimentary layers in the Columbia River mouth as it goes into the ocean and used the sedimentary layers to determine how many floods there were?
That's a very good question. That's one I don't, the answer is no, nobody's done that. But I've long thought that that's what needs to be done to really nail down the number of floods and maybe the timing of the floods. If you had a strategically placed borehole drilled out off of the coast of away from the mouth of the Columbia, you might be able to nail down, or a few strategically placed boreholes, you could nail down the history of the flooding. And that, hopefully someday that will happen, but probably maybe not in our lifetimes.
I have
Thank you.
I have a question. Bruce's territory is back in the Spokane area, and we're into college. And I had my high school years growing up on the Spokane Valley, the bluff above Spokane Valley, foothills. Have you heard of foothills, Bruce?
Is that on the south side?
It's on the north side.
On the north side of the Spokane Valley?
And our little farm was about 400 feet elevation. So tonight I learned from you that the glacial Columbia,
Lake Columbia
actually the Spokane Valley, and so that may have reached that height, but the floods coming down from Missoula, I'm wondering if they reached as high as 400 foot above the Spokane Valley, because
oh yeah, definitely.
on our property, we had a lot of rounded mica schist boulders, huge boulders, and I wonder if that was a product of the floods.
It could have been. The floods went up to Lake Columbia went up to 1,500 feet elevation. So when the Missoula floods came in, they went up even higher than
above the valley floor.
Well, no, that's elevation. I don't know, what's the elevation of the valley floor?
Well, Spokane's about 2,400 feet or so. I don't know.
But anyway, yeah, I'm pretty sure in the foothills that you're talking about, there was flooding up there and there could have been flooding by Lake Columbia, as well as floods coming in from Lake Missoula.
Thanks.
Yep.
Bruce, we're getting a request to have you turn back your video.
Oh, okay.
We miss seeing your face.
Okay. Let me see if I can do that.
I'll turn it back to Carol.
Start.
Okay.
Okay. There we
There
go.
you are. Thank you.
See me now?
Lawrence had a question back when you were talking about the Great Blade, wondering how the blades forming, how are the blades forming between side-by-side cataracts? Is there a hydrological explanation for why these form?
Yeah, that's a good question. I think the power of the floods was focused on either side of the blade. And so the blade was kind of in an area where there were two very strong erosive forces taking place, and that were receding the cataracts. And they've just left behind this protected area in between. I don't know if Vic Baker is still on the line. If he may have a better answer to that, but I don't know. I'm not confident of the answer.
Yeah, I am on the line.
Okay. Yeah.
The cataracts head in a curvature, and so the water flow coming over them gets focused, and the energy is expended, therefore, in the at the focus of the curvature. So it's very difficult to erode through the basalt structure unless you get a cliff. And then, of course, it can undercut the cliff. But if it's just the surface of what's called the entablature above the basalt, it's extremely difficult to erode into it. So these curving cataracts recede headward. And if you have two of them, like you have at Dry Falls, then the area between them is left behind as the cataract recedes. And so it doesn't erode because the erosion is moving beyond where the little residual element is left behind. There's an analogy to the streamlined hills, the so-called loess islands, because once the once the erosion has passed it, just the water just flows past it without further erosion. The basalt erodes by what's called plucking erosion, and that's really the pressure fluctuations in the water suck the large chunks of basalt, the columns and other things out. So when that doesn't occur, then the basalt is resistant, and so the blade, the erosive energy has passed it, and it's left it behind as a residual. Having said all of that, it's something we need to learn a lot more about, because when people try to learn about the mechanics of river flow, they try to make a little model of that in what's called the flume. Well, you can't put a catastrophic flood in a laboratory, so you can't do the measurements. It would be impossible to put instruments in it. So the only other way to deal with it is theoretical, and the flow is of such high energy and the process is so complex that we don't have even now the computational power to deal with the complexity of what was going on during the Scab land erosion. But this will probably happen in the future. Computer power is increasing, and maybe another generation or two of scientists will have the power to figure out the answer to such questions.
Good. Patty was wondering, how did Bretz explain the straight tectonic features of the Scab lands?
Like the HU Ranch Canyon and Devil's Canyon, if that's what they mean. I assume he realized that they were probably tectonic in origin. I don't remember actually reading or him specifically mentioning those, but I can't believe that he wouldn't have known or realized and figured out that they were probably tectonic.
Dennis said your video showed that huge volumes of material were removed from the Scab lands. Was there a lot of resulting deposition downstream, or did most of it get carried to the ocean, the Columbia fan offshore?
Well, a lot of it did end up out in the Pacific Ocean, especially the finer grain material. A lot of the coarser material that's harder to transport would have dropped out sooner onto flood bars. And there's lots of flood bars within the Scab land. A lot of times they're on the downstream ends of these Palouse Islands. Sometimes they're in places like Ephrata Fan and Mattawa Fan, where a lot of that material ended up getting deposited.
And then Lawrence was directing this, I think, to Carol Hassenberg about how do these features look from ground level? Can you see something that looks like the aerial views?
Well, it depends on the feature.
She's
But
got
I think
a picture behind her.
I think, well, the answer is in most cases, the answer is no. Because when you're at ground level, you can't see giant current ripples. All you see is like maybe a small ridge on one side of you and a small ridge on the other, but you don't know whether that's a stream valley you're looking at or something else. So the scale of most of these features is so big that you really have to get up high to see them.
And Bill asks, by looking at some of the features of the Scab lands, can you determine what member of the Columbia River basalt group these features are carved in?
Can you repeat that question?
By looking at some of the features of the Scab lands, can you determine what member of the Columbia River basalt group these features are carved in?
Okay, let's see. Not really. I mean, there are some flows that are distinctive, like the Rosa basalt flow has these big columns, these huge columns that form. And that you can see, when you see these big columns like at Frenchman Coulee or Drumheller channels, you can oftentimes associate those columns with a particular lava flow, but not always. And there aren't too many other instances where I could identify the basalt flow based on the flood evidence.
And Bill also directs this to both Bruce and Vic. Are we finding scabland features on Mars or other planets?
I'll default to Vic on that.
Yeah, the scabland features on Mars were a big surprise to Brett's. He actually lived long enough for the discovery that was made. In 1992, a spacecraft arrived at Mars called Mariner 9, and it was a complete shock to the scientific community because they found large channels on the planet Mars. I mean, these were really big. A channel is a feature long and thin that carried a huge amount of fluid. And when those were found, I had been an environmental geologist at the University of Texas. But as soon as I saw the pictures of those, I recognized that they were analogous to the features in the channel scabland. So I immediately became a planetary geologist, and I've been, part of my time has been in planetary geology ever since the early 1970s. So these features are on Mars, and they are the largest water fluid carrying channels we know about anywhere in the universe. They are much bigger than features in the channeled scabland, but they have many of the same kinds of characteristics as scabland channels. It would be another lecture to even begin to talk about the features on the channels on Mars. But I did a book on them in 1982 called The Channels of Mars. And I've been studying them now, I guess, close to 50 years. So big topic.
Yeah, maybe we could have you back to talk about that sometime.
Yeah, happy to sometime.
Let's see, Lawrence asks, how many feet of soil was deposited in the Willamette Valley from the floods? Tens of feet?
Yeah, at least tens. There have been studies done by other people. There aren't that many good exposures. I mean, there's the Willamette River cuts through, and there's some exposures created by the river that maybe are a few tens of feet. But if they have they probably have boreholes that I haven't looked at that probably would place the contact with the flood deposits down below the river level.
Carol Hassenberg is surmising that maybe the meteorite busted up the ice dam.
Well, yeah, some people think there was only one flood and it was from a meteor impact. But we have good evidence to suggest there were many floods occurring at regular intervals. So that doesn't hold, but considering the size of the ice sheet, it's a quarter-iron ice sheet and it extends way up into Canada. It covers over a lot of the mountain ranges in British Columbia. It's a huge ice dam. So I have a hard time believing a meteor impact would wipe out all the ice at one time.
My
'Cause-
husband
'cause it
and
was so
I
big.
were kind of joking on that one, Bruce.
Okay,
So
all right.
you don't need to
All
worry
right,
about
yeah.
offending me.
Okay, all right. So yeah, I know there are some people that attribute the floods to meteor or comet interactions, but without the evidence to support it.
And then Lawrence was commenting that he's amazed, and I agree that Brett's was able to see this stuff from the ground level and translate it all into what it might look like from an aerial view.
Yeah, yeah, he had an unusual mind to be able to envision what he did. He was able to assemble everything he had seen into 3 dimensions and sit and stand way back and look at it in his mind.
And then he says, I'm interested in how the Lake Bonneville flood was determined to be one flood at 18,000 years ago.
Well, let's see. Jim O'Connor, who was a student at Vic Baker's, and others studied that, and there was no ice dam for the Lake Bonneville flood. It failed when the lake overfilled and spilled over a low pass, the Red Rock Pass, and eroded down into an alluvial fill within the pass. And once it eroded down into that alluvial fill, into the bedrock, then it was shut off. But in the process, it was able to lower the level of Lake Bonneville by, I think, 300 feet. And that's what created the Lake Bonneville flood. But there was after that, all there was that rock ledge and no way for the lake to fail again like it did the first time.
Let's see, Peter asked, do you think there were humans in the Willamette Valley when the last of the floods came through?
Well, that's a good question. There are Indian legends that have been handed down over generations, and suggesting that perhaps there were humans living here at the time. Our Rattlesnake Mountain here in the Tri-Cities, where I live, the local Native Americans have a name called Lalik, which means land above the water. So we're out here in the desert where there is no water except for the rivers. So it's possible that the ancient Native Americans that lived in this area were around during that time. But well, time will tell. There is no solid evidence. There's no physical evidence of humans yet that have been tied to the Ice Age floods.
And Clay is wondering, is there cross bedding in giant current ripples?
Yes, definitely. Most of the cross bedding I've seen are these giant foreset beds that are exposed in borrow pits and various things, and these foreset beds dip downstream in the direction of the flow current, and so there are, and the sets of these giant current ripples or these foreset beds can be 8 or 10, 15 feet thick in places. So it's a massive amount of water that moved and created these foreset beds that he's talking about.
Let's see, Lawrence is asking about flocking erosion. I guess wondering what that is.
Flocking?
Yeah, flocking.
I'm not familiar with that term.
Yeah. Lawrence,
Is it with a U instead of an O?
Flocking. Lawrence, you want to?
No, I'm not. If somebody else knows what he's talking about, I chime in.
You can unmute, Lawrence.
I don't know.
And explain yourself there.
Yeah.
Let's see.
If I may, I think I saw the question come up in chat after he said plucking erosion, how the basalts pluck.
Oh, I see. Yes.
So I might have said pluck. I mean, with a P.
Plucking, P-L-U-C-K.
Yeah, right. Plucking. Yeah, the floods definitely were able to pluck basalt columns. And that's what caused the coulees to erode so quickly, was through this hydraulic plucking.
Oh, let's see what else I can pick out here. There's several comments people are making. Carol's got Devil's Canyon in her background.
Oh, really? The Devil's Canyon is a really neat feature, and it's unfortunately it's hidden from most people. It's there's a public road that runs all the way through it, but there's never been a sign or directions on how to get there. So it is, if you go to the town of Colotis in eastern Washington, it's not far from there, and you could easily find it.
I think we were, this past summer, we took a trip and we used your book as one of the reference guides.
Oh, good.
So we.
Oh, good. Thanks. Yeah, that's kind of why I wrote the books, just to help people find these places.
Yeah.
I like that backdrop.
That's the end of our questions in the chat, and it's close to time to stop the recording, so I'll do that, but I think we can probably stay on if people want to mute or unmute and ask further questions if you're willing to stay on, Bruce. But there's lots of comments. People really enjoyed the talk.
Well, thank you. Good.
Just fantastic.
Good audience. Good audience.